Thanks for the introduction and for the invitation. I'm going to talk about ancient Greek astronomy, about the models proposed, models of the universe proposed by ancient Greek philosophers, but I will not going to talk about the things you probably have heard about before, like epicycles, right? But earlier models. So as many of you probably know, I'm not an expert at all on history of astronomy, but I happened so I was asked to give lectures on ancient Greek astronomy for this master program on liberal arts. And I thought, okay, sure, I can do that. It's easy. I know about it. I was thinking about the size of the Earth, you know, the usual stuff, the geocentric model. But then I realized that this couple of lectures were actually several hours long in total, and that the program in general was much deeper, right? So I had to go deeper myself than the usual Astro 101 that I knew about. So I learned a lot, and I thought it would be interesting to share some of that with astronomers as yourselves. So this area is actually, there's a lot of active research, because we don't have, there is no a clear picture of what different philosophers thought at the time. And we have a few fragments only of their text. We have text written by other people, in many times their competitors. And so we have a very confusing account in total. And so it's not easy to reconstruct the models. And I checked a lot, several, let's say, books and articles. But I wanted to highlight these three because they were the most important for what I'm discussing today. So two books by Dirk Kaupri on, well, mostly that I'm going to discuss on the first part. And the second part is this book on the astronomical system of Aristotle by Gerardo Botteri and Roberto Casassa. I couldn't find a picture for the first of them. Okay, so this is the archaic view of the universe. This is what most people consider the structure of the universe. I don't know, more, let's say 3,000 years ago. And of course, there was a flat Earth. That was the most sensible assumption. And there was a firmament, which was this dome, like a hemisphere, right? Where all the planets, all the stars, the sun and the moon were located. Maybe they could move within the firmament, but they were stuck there. And that was it. We had no way of going outside this hemisphere. And below and behind, below the Earth and behind the firmament, there were mythical things only, like, I don't know, heaven of heavens, the pillars of Earth, the underworld. Those were not really part of our physical universe. And so what I show here is like what the Bible says, right? But also the Egyptians had the same kind of ideas. And this picture is actually quite interesting because it shows the sun, what the sun does during the night. So the sun is swallowed by this goddess, the goddess of the sky, And it goes back to the east, like inside the sky, inside the heaven. There's no underneath the earth. There's no path underneath the earth. And then the sun gets born again in the morning the next day, and crosses the sky. So during the day, it crosses the sky where we can see it, and during the night, it also crosses the sky, but like inside the goddess, so we don't see the sun. And this dome, this firmament, in some depictions, it needs a support. It needs, for instance, here is Shu, an Egyptian god, that is supporting Nut, the Egyptian goddess, the goddess of heaven. And this support is needed because the firmament is like a physical structure, and it could fall. And actually, that idea was familiar to me from childhood, right? In Asterix, the very brave Gauls are only afraid that the sky could fall on their heads. And yeah, if the sky is something that is like this roof, it could fall. So to go beyond that that conception, we need a physical model, a mechanical model, and the first one that we know of that made such a model was Anaximander in the 6th century BC. So Anaximander was a philosopher, but also a geographer. He created the first realistic map of the world. So that was the known world back then: Europe, Africa, Asia, right? And surrounded by an ocean. And it doesn't look very realistic to us, but if you compare this to earlier maps were not maps at all. It was just a very schematic representation of the world. This was a very modern map in a way. And so he was making measurements using a gnomon, for example. He was studying the dates of the solstices, equinoxes, and so on. And with all this knowledge, with all these techniques he had developed, he was able to, as this famous picture shows, he was able to go to observe like behind the firmament and see which were the mechanisms operating behind. So for Anaximander, as for everybody, or pretty much everybody during that period, the Earth was flat, but he already gave it some more physical structure. So it was like a drum, a cylinder, a short cylinder. And so this is the Earth, right? Now we see the Earth here, and the Sun and the other celestial bodies are these wheels. So it's not that the Sun moves on a wheel. The wheel is the Sun. This whole thing is the Sun. And there's a little hole, which is where we see the light of the Sun coming to us. So it's a very weird to us way of looking at things. But it makes a lot of sense, because you don't need any structure to support the Sun. The Sun is this whole thing. And as I said, the moon is its own wheel, and in principle, every star, every planet is a different wheel. And all of these wheels are rotating around the Earth. They do it once a day. Therefore, the hole they have, where this aperture, where we see the light coming to us, moves around us on the sky. And also, the wheel of the sun moves along its axis, and that creates the seasons. So when the wheel of the sun wheel, let's call it, is higher along its axis, it was summer. When it's lower, it was winter. So the sun would spend more or less hours, the light of the sun would reach us, let's say it that way, for longer or shorter hours, depending on the time of the year. I'm going to show you this. Is it running? Yeah, it is running. Very beautiful animation I took from this website, thehistoryofphysics.org, in which we can see the whole model, right? Here is the Earth. Notice that the Earth is floating. It's on space in the middle of nothing, right? And apparently there were some like symmetry arguments to explain why the Earth didn't move. It was right at the center, so therefore it had no reason to move anywhere. And yeah, the Earth is surrounded by the different wheels. Here we see the wheel of the sun. As I mentioned, there's this aperture, which is where we see the light of the sun coming from. And that aperture can be closed. And that's how eclipses were explained. Similar thing for the moon. And it's not very clear, but apparently this sort of closing of the aperture could explain both lunar eclipses, but also the phases of the moon. And both wheels are rotating around its axis, their axis, right? Making the daily motion of sun and moon on the sky. And moreover, they move along their axis. In that way, in particular for the sun, creating the seasons. So what I wanted to emphasize here is that for the first time, we see that the universe, that the world is an unbound domain. It's a three-dimensional place where we have these physical objects. So we live with this model, we leave behind the idea of a bound place in which there's the Earth, there's the celestial bodies, all within this two-dimensional hemisphere. Sometime later, about during the next century, the 5th century BC, we have Anaxagoras, and Anaxagoras had the idea to explain or to interpret the celestial bodies as fiery stones. It gave them a physical nature. So, and not a magical ether-like nature, but a very concrete one. So these were like stones that were burning somehow. And they surrounded the Earth, and the Earth was like a very, very flat, very thin surface that was floating as a leaf would float on the wind. And actually, he could even explain earthquakes as vibrations due to this wind. Now, this same wind would be much stronger further away from the Earth, and there was like a vortex motion, like a tornado or a whirlwind, that made everything rotate around us. So the sun, the moon, the stars, the planets. And because of this rotation, because of what we could call centrifugal force today, they didn't fall. But it was not a very stable situation. It's like a vortex moving things around, and sometimes things would fall. One object from the sky could fall on Earth. And this was very timely because at that time there was a very big meteorite that fell on Potami, a place nearby. And this is not a picture of that meteorite. That meteorite is now lost, but the descriptions we had indicate something of about this size, a few meters size. And this is really interesting because this rock fell from the sky, so it could be a piece that fell from the sun, from the moon, perhaps the result of a collision between planets that were stony, or stars, right, that were made of stone. And here there was a burning stone falling from the sky. He also proposed the first explanation for the Milky Way, in which the Milky Way was considered as formed by stars. So we see a lot of light in the Milky Way, in the region of the sky where we see the Milky Way. We see a lot of light there, this diffuse light, because there's very many stars. And that's roughly the same explanation what we have today. But what is interesting is that it was not a physical effect, but rather optical thing, an optical effect. The region where we see the Milky Way is the region, according to Anaxagoras, where the Earth blocks the light from the sun. So we see more stars here because we are not blinded by the light of the sun. Elsewhere, we see fewer stars, only the brighter stars, because the light of the sun doesn't allow us to observe more stars, fainter stars. Of course, this is unphysical. We know that nowadays, but there was no clear understanding of optics or of the nature of light back then. So it was somewhat, it was reasonable. There's also an interesting explanation for the darkness of the night sky. I mean, if this part of the sky was illuminated by the sun, why do we see it dark? And apparently the explanation was that the sun was too far. So there was enough light to prevent us from observing fainter stars, but not enough to make the sky look bright as during the day. Anaxagoras also studied the nature of the light from the moon, it is apparently he wrote that the moon receives light from the sun. So modern astronomers would understand that in the modern sense, right? That the moon is reflecting light from the sun, but that wouldn't be consistent with his picture of the Milky Way. If we believe his picture of the Milky Way, then the moon would be eclipsed. There would be a lunar eclipse every time the moon coincides with the Milky Way, and that is not the case. So this idea of him realizing that the moon reflects light from the sun is inconsistent with what he wrote about the Milky Way. So most likely, when he said that the moon receives light from the sun, it's not in a reflection way, but in a more how to say, chemical way. The moon is not illuminated by the sun, the moon is kindled by the sun. How can we understand that? Well, when there's a new moon, the moon is close to the sun. That was an obvious fact. And therefore, if the moon is close to the sun, it can receive, like directly, physically, it can receive heat, fire, whatever you want to call it, from the sun, just because it's nearby, and it gets kindled, and it starts burning. And because it is made of stone, that burning is slow, it takes time. So at the beginning, you start a little fire in the part that is actually closer to the sun, and that fire spreads, and the moon gets slowly more and more illuminated until the whole moon is burning. And then it runs out of fuel, something like that, and it starts getting darker again. And of course, then the whole cycle starts again. Besides studying the nature of different celestial objects, Anaxagoras also calculated the size of the sun. And his conclusion was very surprising. It sounds very surprising for us today. He said that the sun was roughly the size of the Peloponnesus, this big peninsula in Greece. And this was like a mystery, right? How he came up with that number, with that size. And well, Taupri, one of the authors I was referring to at the beginning of my presentation, he actually argues that this is a very sensible result if you do the experiment of measuring the shadow of a gnomon placed in different places. For example, in Sparta and Delphi, two places in Greece separated by 150 kilometers or so. And since they are at different latitudes, you would measure a different length of the shadow of a gnomon. And this is very much the same measurement that Eratosthenes did a few hundred years later. But there's a huge difference on the assumptions. While Eratosthenes already knew that the Earth was a sphere, since he knew that, he would interpret the measurements in a very different way and measure the size of the Earth. But if you assume that the Earth is flat, you have a different geometry, and then you interpret these measurements as giving you the distance to the sun. The sun is not at infinity, as it is assumed when the Earth is flat. Therefore, the sun rays are all parallel to each other. Here they come at different angles, and therefore one can calculate the distance to the sun. It's a relatively short distance comparable to the size of the Earth. And once you know the distance to the sun and measure its angular size on the sky, one can get the physical size of the sun, which is about 100 kilometers. So this is really interesting how the same experiment can give you a very different result depending on the underlying geometrical assumption. I'm going to move now to the Pythagoreans. They were some sort of sect, you could say, a religious, philosophical movement that believed that everything was made of numbers, and they kept their results very secret. So it's not very, there's a lot of obscure details, but they developed a very interesting cosmological model or system. Apparently it was developed by Philolaus in the 5th century BC, and they were considering the Earth already to be a sphere. This was mostly because they believed that the sphere was a perfect shape, right? So things had to be made out of spheres. And they had the Earth rotating around the big central fire. And this big central fire is not the sun, as you may think. The sun was also rotating around the fire. And I'm going to show you an animation that I think it makes it clearer. So this is the Earth. This is the big central fire. And notice this red arrow is showing where we are. The Earth is, we would say, tidally locked. Its rotation and its orbit have the same periods. So we're always looking away from the central fire. The Earth inhabitants can never look at the fire. And this period is 24 hours. So everything moves around the Earth on the sky every 24 hours, roughly. That's the Earth evil twin, not necessarily evil though. That's the counter Earth. It's also between the Earth and the central fire, so we never see it. And the reasons for having it are not perfectly clear. Maybe something to do with the harmony of or the frequencies involved, or the number of objects. But in any case, it's always out of our sight. And both the sun and the moon are also rotating around the central fire. The moon goes around once a month, the sun once a year, and in that way, their motions compared with the background with the stars can be explained. I'm going to discuss now about the developments made by Plato's followers in the academy. This was later. This was in the 4th century BC. Here there was already a strong influence of this idea of things had to follow geometrical or mathematical shapes, the sphere being the most perfect of them all. Here you can see a few philosophers with what seems to be a celestial sphere and a sphere of the earth. And that was all very nice, but they knew that things were not fitting easily with the observations. So as you know, planets do not move on the sky with a circular uniform motion. They actually turn around and have these periods of retrograde motion. So apparently Plato challenged his students to come up with an explanation of how this can happen if the universe is made with spheres, circles, and so on. And the one who managed to provide an explanation was Eudoxus, who realized that if you have two spheres in which one of them is like stuck in the other one, but with tilted axes, their axes do not coincide, and if they rotate with the same period, you make this sort of loop, this number 8 or infinity shape. So I'm going to show you another animation from the history of physics.org. Here you can see the two spheres. They rotate with the same period, but their axes are tilted. And that's how you can make one planet create these loops. Of course, that's not enough. The planets also move along the ecliptic. So to do that, you need a third sphere. That's the blue sphere that is shown here. So if you put these three spheres together, you recreate the motion of a planet as you would see it if the stars were fixed. But this is actually not enough, because we also see that the planets, same as the sun, the moon, and the stars, move around the Earth apparently every day. So for that, you need a fourth sphere, which makes everything moves every 24 hours. It moves the whole system every 24 hours. So with four spheres, one can explain roughly the motion, the whole apparent motion of a planet. So one sphere for the daily motion, another sphere for the motion along the ecliptic, and two spheres for the to make the retrograde loops. This same scheme can be applied also for the moon and the sun. So for the moon, we have one sphere for the daily motion, another sphere to make the moon move along its plane, what we call now its plane, which is tilted with respect to the ecliptic, and an intermediate sphere that makes this plane of the moon precess. That precession was already known at the time. The same for the sun, although the sun moves by definition on the ecliptic, right? So it's not clear exactly why there was this intermediate sphere. The precession of the ecliptic was not known at the time. So it seems that this intermediate sphere was put there as an analogy or a generalization from the moon. I'm going to skip what Callippus did. He basically refined this model, and going to jump to Aristotle. While Eudoxus gave us, we could say, the kinematics of the universe, a description of how everything moved, Aristotle was more interested on the dynamics, why they moved. And just let me say a few words of what were his assumptions. So the basic laws of motion. So actually there were two sets for earthly objects around us. The massive objects, we could say, they fall straight down. That's what they do. And objects in the sky, celestial objects, they move in circles. So there's two sets of physics laws, depending on whether you are in the heavens or on the earth. And this explanation, this law actually nicely tells you why the earth doesn't move and why the earth is spherical. Basically, everything massive falls to the center of the universe. And if all the rocks in the universe fall to the center of the universe, they end up forming a sphere, and that sphere is the earth. So that's your explanation for the shape, the position, and the apparent lack of motion of the earth. And I really like this animation because it almost looks as a simulation of planet formation. It's like a self-gravitating process in which things fall onto each other and end up forming a planet. As I said, Aristotle was interested in the mechanics or how things would force each other. And there's this concept of prime movers, which became related to theology, the reasons for motion and so on. But the point I want to concentrate on here is that for him, the spheres were real objects. It was not only a mathematical abstraction. So if you had some spheres and those spheres move things inside, then if you have another planet closer to the Earth, that planet will also be affected by the spheres further out. So he invented the unrolling spheres. So you had to reset the motion in a way. So for each set of spheres that make a planet move, you need a set of spheres to undo that motion. So let's say these are the spheres that move Jupiter. You need another set of spheres to reset the motion so Mars can start fresh. So these spheres will set the motion of Mars without being affected by the motion of Jupiter. All in all, Aristotle needed a lot of spheres to explain the motion of all the planets, the moon, and the sun. The actual number is actually debated by this interpretation by Botteri and Casazza claims 55 spheres were needed. So my time is up. So let me give you a brief summary. I'll try to show you some steps in which the archaic view of a flat Earth surrounded by this firmament was superseded by scientific, what we could call scientific explanations. First, Anaximander put a mechanical device. You imagine the universe as a mechanical device that existed in 3D, right? And explained the motion that we see on the sky. And Anaxagoras gave not realistic perhaps, but natural composition to the celestial bodies, and that was related, at least in the case of the moon, with how it was illuminated. The Pythagoreans apparently for the first time thought of the Earth as a sphere, and they had a very ingenious mechanism to have all celestial bodies make a 24-hour cycle. And finally, Eudoxus and his followers or students could explain with concentric spheres the complex motion of all celestial bodies on the sky, including the retrograde planets. Although ironically, in doing so, they had to put this celestial sphere that made the universe bound again. They also had different, Aristotle in particular had a more magical or mythical explanation for the composition of the celestial bodies. And also the 24-hour cycle was not explained naturally. It had to be put again by hand for each object. I think that's it. Thanks for your attention.